Hello students, welcome to the series of lectures on digital speech processing. In this video, we would like to see the classroom discussion topic on frequency domain representation of a homomorphic system for convolution. So in the last video, we have already seen the introduction part of the homomorphic system. What is the main purpose of the deconvolution? Okay, like that we have already seen in the previous video. Now in this video we are going to be looking for the domain, the frequency domain representation of the homomorphic system. So let's get started. Alright, so this is the lecture learning outcome. So on completion of this lecture you will be able to understand the discrete time Fourier transform representation of a homomorphic system for convolution. Alright, so this is an introduction part. We clearly mentioned, the first point I have mentioned in this slide is that, so we know that the speech can be represented as the output of a linear time varying system and whose properties are slowly vary with time, because speech is a non-stationary signal. So this problem of the speech analysis is to estimate the parameters of the speech model and to measure their variations with the time. It is very biggest challenging task for us. Okay. So this problem is often called as deconvolution. Now, when you see the canonic form for the deconvolution using the discrete time Fourier transform, so this is the block diagram representation of the discrete time Fourier transform. Okay. So what is the first block here? The first block is the logarithmic block. Second block is the linear operator in the frequency domain, and third one is the exponential. Okay. So what we are going to be doing here is that first we need to find a system which converts convolution to addition. Okay. So convolution to addition that we need to convert. Okay. That is a homomorphic system. We clearly mentioned that. And x of n equal to x1 of n star x2 of n, where if you want to convert that into the another domain like frequency domain, and this convolution becomes multiplication in other domain. Okay. And since the d star of x of n, because this is a characteristic system that we have already seen in the last video, so will be nothing but this convolution becomes the addition. X cap of n is nothing but the complete system for this characteristic system. And when you take the frequency domain representation like that, and you'll be having x1 cap of e power j omega plus x2 cap of e power j omega. Okay. And after that, what we are going to be doing is that, so this becomes the input to the linear operator. And before that, what we are doing, we are going to be using the logarithmic functions, and which converts product to the sums that we already know. So the product it is going to be taking as x1 of e power j omega into x2 of e power j omega, and whose output nothing but the addition. Okay. So this this multiplication becomes addition when you apply logarithmic function. Okay. And this is considered as an input to the linear operator, and there you will be getting the y1 cap of e power j omega plus y2 cap of e power j omega, and this will be input to the exponential function, and you will be getting so this additive will be converting into product. Okay. So this is the way how we are going to be looking for the canonic form for the deconvolution using the frequency representations. Now, so when you want to see the characteristic system for the deconvolution using the Fourier transforms, so this is the way how we are going to be doing that. So we are taking the x of n, and which is a convolution property, and when you apply the Fourier transform, it becomes a product, because convolution in one domain equivalent to product in another domain. So there you will be getting x of e power j omega. This becomes an input to the logarithmic function, and this is nothing but the product will be converting into the additive property. Okay. So x cap of e power j omega will be getting, and this becomes the input, and the third system is the inverse of the first system, right? So there you will be getting the x cap of n. So this x cap of n nothing but this is the inverse Fourier transform of the logarithmic of Fourier transform. Okay. So normally this we are calling as a cepstrum. So that we are going to be seeing in the next slides. This is a very important parameter in the speech processing model. Okay. So this x cap of n is nothing but, we can clearly say that it is an inverse Fourier transform of logarithmic of the function. So now, similar way, the way how we are going to be calculating the D star, now it is exactly the reverse of that. So inverse characteristic system for the deconvolution using discrete time Fourier transform. So here what we are doing, the first system is the same thing, the way how we have already taken into consideration in the previous. So Fourier transform we are taking, and the second system, instead of logarithmic, this is an exponential, and the third one is the inverse Fourier transform of the first system. Okay, so this is the way how we are going to be getting the y of n, where y of n nothing but an inverse Fourier transform. And here we are, what we are doing, instead of taking the logarithmic, this is an exponential function we are taken. Okay, so this is the way how we are calculating the y of n. Now, and similarly we can also, so in the previous two slides we have considered the Fourier transform domain. Now when you consider the jet transform domain, because in the frequency domain either you can consider Fourier transform or you can also consider the jet transform. If you consider jet transform, this is the way how we are going to be looking. Okay, this is the first system, this is the second system, and this is the third system. Okay, so this is the way how we are converting x of z as an input to the y of z, that is an output of the complete system. Okay, now, and similarly, characteristic system, how we are going to be taken into consideration, but that is d star of something when in Z transform domain. Okay, this is the way how we are going to be considering. So x1 of n convolved with x2 of n, that becomes the product, and this product becomes the additive property, and this additive property is again additive property, but this is a IZT. Okay, instead of taking IFT, this is IZT, inverse Z transform. Okay, you'll be having x1 cap of n plus x2 cap of n. So this is the way the mathematical expression should be looks like. And similarly for the inverse characteristic system for the deconvolution, when you want to consider the Z domain, this is the way how we are going to be looking. Okay, so this is the y of n. Now the properties for characteristic system. When I say the characteristic system, it is nothing but the d star of something. Okay, so this is nothing but the characteristic system. Okay, so x cap of n is equals to d star of x of n is equals to d star of x1 of n convolved with x2 of n. Okay, and when you apply separately to that, and you will be getting x1 cap of n plus x2 cap of n separately. And similarly for the inverse characteristic system property should be like this. Now, so before we consider what is the substrum, I clearly mentioned this is the inverse Fourier transform on the logarithmic spectrum, and this is the terminology that we are going to be looking here. The spectrum that we already know, it is the Fourier transform of the signal autocorrelation. Substrum nothing but the inverse Fourier transform of the log substrum. Okay, so this is the way how we need to understand the terminology. Okay, in one domain to the other domain. Now, so our focus is only towards the understanding of the substrum. So the term substrum, which was introduced by Bogat and has come to be accepted terminology for the inverse Fourier transform of the logarithmic of the power spectrum of a signal. Okay, and the term complex substrum, which implies the complex logarithm is involved. So if logarithm is complex, that we are calling as the complex substrum. If logarithmic is real, that we are calling as the real substrum. Okay, now, so how we need to compute the substrum? So this is the way how mathematically we can represent. So C of x of t, where x of t is the time domain signal, is equals to, I clearly mentioned, this is the inverse Fourier transform of the log of power spectrum. So f inverse of logarithmic of Fourier transform of time domain signal. Okay, so when you apply Fourier transform to the time domain signal, that nothing but the spectrum only. And when you apply the logarithmic, that becomes the logarithmic spectrum. And when you apply inverse Fourier transform, that becomes the substrum. This is the way how we need to compute the substrum. Now, how we need to visualize the substrum? Okay, so this is normal time domain signal x of t. Okay, so let me write this is the first signal is the x of t signal, and when you apply DFT, and you'll be getting the DFT of that, the spectrum will be there. And when you take DFT as an input here, this is the third one. When you apply logarithmic, so this is the log of power spectrum we will be having, and this log of power spectrum as an input. Okay, so this is the fourth system. And when you apply inverse discrete Fourier transform, and you will be getting the cepstrum. The same thing. How we need to compute the cepstrum is nothing but inverse Fourier transform of logarithmic of Fourier transform of x of n, where x of n is our time domain speed signal. So this is the way how we are analyzing the cepstrum. Okay, but what you need to understand, but what is the x-axis that we need to consider? Okay, on y-axis, of course, there is no ambiguity here. The absolute magnitude that we are going to be taken into consideration. But when it comes to the x-axis, what thing we need to understand? So this is nothing but Q frequency, because frequency in one domain will becomes Q frequency in the terminology that we have already seen. Okay, but it is in hertz, but it is in milliseconds of the order. Okay, that way you need to understand. Now, so this we clearly seen that one peak is there. So this I am calling as the harmonic in one domain. But when it comes to the cepstral domain, so in the cepstral domain we are calling this is a ramonic. Okay, so that we are calling as a harmonic in spectrum domain. But when it comes to the cepstral domain, we are calling that is ramonic. So this is the first harmonic. Okay, and now when you understand the spectrum, like this is the logarithmic spectrum, that is speed signal, and the spectral envelope is be there. So these indicate the peaks of the signal we are calling as the formants. Okay, so there are so many peaks. I will be having this is a formant F1, formant F2, formant F2. These are nothing but which carries the identity of the sound, or nothing but the resonant frequencies also we can call. Okay. Now, so how we need to formalize the speech is nothing but when you take the logarithmic of the x of t, and you'll be having the logarithmic of e of t, that is the excitation, and then system response. The way how we have already seen that for any system, excitation is input, excitation is nothing but the impulse response, and if you want to take what is the output of the system, this is the convolution of excitation into multiplication of system response h of n. Okay, so when you apply the logarithmic, this is the way how we are going to be. That multiplication will be converting into product. That product will be coming into additive property. That is the way how we are going to be looking. Okay, so this is a normal speed signal, and this is the vocal tract frequency response, and this is the glottal pulse. Okay. Now, what is our goal actually? We need to separate the components. What components we need to separate? The system function components and then glottal pulse. Okay, or nothing but the excitation. So this we are going to be removing. We are going to be taking the system response. So this is the system response which can be used to estimate each and every parameter of the signal. So that way we are going to be considering this. Okay. So now what we are doing is that we have already know x of t equal to e of t plus h of t. So where h of t nothing but the system response, e of t nothing but the excitation. So what filtering technique we need to apply? Normally in the spectrum domain we are calling that as a filtering technique, but when it comes to the cepstral domain we are calling that as a liftering. So we need to apply liftering. We need to remove the high frequency components and we can allow only the low frequency components of the signal. So that way we are going to be separating the components. Okay. Now, so this is a high frequency component. The excitation is a high frequency and the system response is a low frequency. This we are going to be calling as a desired signal. This is the undesired signal. So this we are going to be removing by applying filtering. Okay, in the spectrum domain, but we are calling in the cepstral domain that is a liftering. Okay. So thank you for watching this video.